In this video, I'll show you how to integrate a multivariable function numerically using the Monte Carlo integration method. So over here, you're looking at the Monte Carlo casino, but we're going to use a slightly different method to integrate some simpler functions first. All right, so let's look at this simplest function here. It's single variable. It's e to the power of negative x. Its integral is simply negative e to the power of negative x. If we integrate this from 0 to 1, the result is simply 1 minus 1 over e. So it's right here. 1 over 1 minus e to the power of negative 1. Okay, so that's the exact expression. And this is the integral value. But we're going to use the numerical method to integrate this function. How do we do that? Because we're going to integrate this function from 0 to 1. The range is 1. I will divide this range into 5 parts, from 0 to 0.2, 0.2 to 0.4, 0.4 to 0.6, 0.6 to 0.8, 0.8 to 1. And then I find the midpoints of each of the 5 bins. Okay, so this 5 are 5 midpoints. And then I will just evaluate the value of this function e to the power of negative x at this position, 0.1, at this position. So 5 positions. How do I do that? Okay, over here, this is simple. It's easier to evaluate the value of a function. It's more difficult to evaluate the integral of the function. That's why we are doing this. All right, 5 midpoints and 5 function values. You can just do this. And over here, what is this? This is 0.2 times this value. Why? Okay, over here, this 0.9 is the height of the bin, but we also need the width of the bin to get the area of the bin. So the area of the bin is 0.2 times the function value. The area of the second bin is 0.2 times this function value, etc. Therefore, we just use 0.2 times the function value here, and then we click this, we drag it down to get the areas of the 5 bins. And then if we sum up the 5 areas, it's going to be approximately the integral value of this function from 0 to 1. All right, so this is the sum of these 5 areas. All right, compared to the exact value, they are pretty close. All right, they differ by only 0.001, so that's very good. Less than 0.1% error. Again, I want to emphasize this. I was using the area of the first bin to approximate the integral of this function e to the power of negative x from 0 to 0.2. It's not accurate, but somehow I underestimate the integral from 0 to 0.1, and I overestimate the integral value from 0.1 to 0.2. So somehow this, underestimate, this overestimate, cancel mostly. So it's not too bad. And then I do this for the entire range from 0 to 1. We sum it up. Some error is canceled. Therefore, the final result is not too bad. Again, compared to the exact value, the difference is 0.001. It's actually less. It's less than 0.2%. It's pretty good. How can we improve the accuracy? We just need to create more bins. I'm going to just divide this 0 to 1 range into 50 bins instead of 50 bins, okay? So the first bin is from 0 to 0.02, and this is the midpoint, and all the way to the last one. The last bin is from 0.98 to 1.00, and this number is the midpoint. And I just evaluate the function value for the midpoint of every 50 bins. And then I'm going to get the area of this 50 bins. The width of the bin is 0.02. The height of the bin is the function value. So we do a multiplication, and again, you can drag it down, drag it all the way down. All right. There are 50 rows. Let's look at the result. We sum it up, 50 rows. We got 0.63211 compared to 0.6212. Look at these two numbers. This is the exact value. This is numerical integration. And they differ by only 10 to the power of negative 5. Really good. All right, so it gives us confidence that it's possible to numerically integrate a in this case, a single variable function. So now, multivariable function, e to the power of negative x minus negative y. Actually, it's possible to integrate this analytically because we can separate this x from y. This is the product of e to the power of negative x and e to the power of negative y. So basically, this integral is the product of two single variable integrals. And the value of each of the two single variable integrals is, well, simple. It's actually 1 minus e to the power of negative 1. So we just need to square it. The result is 0.3996. That's the exact value of the integral of this. Okay, not exact, but it's pretty close to the exact value. Now we're going to use the numerical integration. We got the sum here. I want to show you the sum here. We're summing up the numbers in 25 rows. Why 25? Okay, still we're going to create 5 bins in the x direction, but we need 5 bins also in the y direction. So now we have actually 5 times 5, 25 bins. All right, so x is from 0 to 0.2, 0.2 to 0.4, 0.4 to 0.6, 0.6 to 0.8, 0.8 to 1. Same for y. That's why we have this 5 midpoints here, corresponding to the 5 bins in the y direction. But over here, I'm holding x constant, 0.1, and then I'm changing x. X is now 0.3. How about y? Y can be these 5 values, and then I'm changing x. Y can be these 5 values, and then I'm changing x again to 0.7. Y can be these values, and then I'm going to evaluate this function e to the power of negative x minus y for every single data point. So over here, it's exponential function of negative x minus negative y minus y. Okay, hit enter, and then we drag it down. This time, how many rows? 25 rows, because 5 data points in the x direction, 5 data points in the y direction. We have a total of 25. 5 times 5 bins. And now I'm going to show you this areas of this 25 bins. I put these areas in the double quote because, yes, the height is still the function value, but what about the width? Now the width is not simply 0.2 because the width now, in this case, is actually the width of x times the width of y. So it's 0.2 squared times the functional value. So I want to let you imagine this area has a height and a width. The height is the function value, but the width is actually the width of x times the width of y. All right, so it's a hyper width. All right, and then we're going to just evaluate those areas, 25 of them. We sum it up. We got a integral value of this function. By using the numerical method, it's pretty close to the exact value, so not too bad. All right, but this time I'm not going to use 50 bins for x and 50 bins for y. Why not? 50 times 50, you know, it's going to be 2,500. There'll be 2,500 bins, and we'll have to create 2,500 rows for such a simple function. Okay, now you can imagine, what if we have 6 variables? It's going to be 5 to the power of 6. That's going to be 15,625, I think. Okay. And also, what if we have a function that's changing more dramatically than this function? And then maybe it's not reasonable to just use the midpoint, the function value of the midpoint, to estimate the area of the bin. I don't know. So let's look at a truly complex function here. Okay, we're going to integrate this xy plus 2yz plus 3zx and times e to the power of negative 4xyz. I designed this function intentionally so that you cannot get the analytical value of this integral. There's no way to separate this triple variable integral into single variable integrals. No way. We can, of course, use Wolfram alpha to get the numerical value, very accurate numerical value. So I'm still putting exact here, so it's almost exact. And then we're going to use the same numerical integration method here to get this number. Again, you can see these two numbers are pretty close. Okay, how did I do this? Well, simple. Again, 5 bins for x, 5 bins for y, 5 bins for z. First look at z. Again, 5 bins. The first bin is from 0 to 0.2, and then 0.2 to 0.4, etc. And then y. How about y? Y can also, again, be from 0.02, and the midpoint is this. And then from 0.2 to 0.4, we have the midpoint here. This is the midpoint between 0.4 and 0.6, and so on. And then after we enumerate y, we have to enumerate x, okay? So x becomes 0.3, x becomes 0.5, 0.7, 0.9. Okay, there are 5 times 5 times 5 equals 125 rows here. So that's 125 data points, 125 bins. Look at the height of each of the 125 bins. That's easy. We just need to evaluate the value of this function at this data point. 0.1, 0.1, 0.1. We just type up this function in Excel. Excel will do the calculation for us. Again, you can just double click this filled little square here, okay, to fill out this 125 rows, or you can just click this and drag it down. All right, so I'm gonna just drag it down. All right, cool. And then we're gonna get the double quoted areas of this 125 bins. So again, it's double quoted because true, the height is still the function value, but what about the width of the bin? The width of the bin is actually 0.2 times 0.2 times 0.2. So you have to imagine the horizontal axis is actually a 3-dimensional axis consisting of x, y, and z. So it's 0.2 to the power of 3 times the function value. What if we have 6 variables? It's going to be 0.2 to the power of 6 times the function value. All right. What if I have 30 variables, and then 0.2, if that's the bin width in each direction, it's going to be 0.2 to the power of 30 times the functional value. All right, so we're going to do this. Double click to fill up the 125 rows, and then we sum it up, 125 numbers. Okay, so this is the sum of 125 numbers. You can see here, and it's not too bad. All right, it's not too bad, but we can do better. How do we do better? Very simple. We can have 50 bins in each direction. All right, 50 in x direction, so that the bin width is only 0.02. And then we're going to just use the function, this function, times the bin width, 0.02, to approximate the integral of this function between 0 and 0.02. No, that's impossible, because we'll have to use 50 times 50 times 50. It's going to create 125,000 rows, and I just don't want to do this. All right, so is there a better way to do this? Especially if we're talking about a higher dimension integrals in quantum mechanics. If we have a hydrogen molecule, there are 2 electrons. Each electron has 3 coordinates. Now let's talk about x, y, z coordinates. We have x1, y1, z1 as the coordinates of electron 1, x2, y2, z2 as the coordinates for electron 2. And what about the repulsion between electron and electron 2? How do we get the repulsion? We use quantum mechanical postulate 4. We integrate the total wave function of these 2 electrons times 1 over the distance between the 2 electrons, and then times the wave function again. We integrate that with respect to x1, y1, z1, x2, y2, z2. It's a sextuple integral that contains 6 coordinates, And there's no way to separate those 6 coordinates. How do we do this? Okay, let's say, well, why don't we just create 5 bins in the x direction? No, it's not going to work because you have to create 5 bins in each of the 6 dimensions. Okay, you have to do 5 times 5 times 5 times 5 times 5 times 5. It's 15,625. And still in the end you get a very rough number. Okay, it's probably not going to be trustworthy. You have to use more bins to get more accuracy. But what if I use 10 bins for each coordinate? It's going to be 10 to the power 6, where I have to create 1 million rows. All right, for x1, y1, z1, x2, y2, z2, we need to create 1 million rows. And we need to evaluate the function. What function? Actually, it's actually the wave function of the 2 electrons times the repulsion term. That's 1 over r12 times the wave function. And then we need to evaluate this function 1 million times. And then we can somehow get the expectation value for the repulsion. But imagine 1 million rows. We cannot do that. What if you have 9 electrons? What if you have 100 electrons? When you have 100 electrons, you have 300 coordinates. All right, 300 coordinates. And then for each coordinate, let's say just, 10 bins. And then we're looking at 10 to the power of 300. 10 to the power of 300 rows for only 100 electrons. It's impossible. So I'm going to show you this so-called Monte Carlo integration. All right. This method is really, really good and really, really accurate for those high dimension integrals. But I want to show you a simple example first. This is my simple example here. Again, this is xy plus 2yz plus 3zx times e to the power of negative 4xyz. So I give you this function so that you cannot separate this function into the product of 3 single variable functions. All right. So no cheating here. There's no way to integrate this analytically, but again, I use Wolfram Alpha to get a very accurate number, 0.3623. That's almost exact. And then I'm going to use this quantum Monte Carlo method to estimate its integral value. So this is what I did. I'm still going to do 125 rows, okay? But later you're going to see, well, although we need 125 rows for this 3 variable function, we are not going to use many more data points for a 6 variable function or 9 variable function or even 300 variable function. All right, so that's the good part. All right, so if you use the previous numerical integration with bins with the same width, okay, so the number of bins actually grows exponentially. Again, if you have only 1 coordinate, you have 5 bins. 2 coordinates, 25 bins. 3 coordinates, 125 bins. 4 coordinates, 625. And then 5 coordinates, 5 coordinates, 5 to the power of 5. That's 3,125. 6 coordinates, 5 to the power of 6. All right, that's going to be 15,625. So it grows exponentially. But if you use the so-called Monte Carlo integration, it's not going to grow exponentially. It's going to be much slower than that. So I'm going to show you this simple example. So I do 125 random sampling over here. What is random sampling? I create a random number for x equals rand parenthesis. That's going to give me a random number from 0 to 1. All right, so if I click this, again, same function, but different number. Over here, same function equals rand parenthesis. That will give you a number between 0 to 1. All right, so this is what I did. Just same rand function. All right, and I'm going to drag it here. And I'm going to create new random values from 0 to 1. All right, so that's it. What if you need a range from 0 to 2? Well, very simple. You just type equals 2 times rand parenthesis. What if you need a number between -1 to 1? Very simple. You just need to have 2 times this random function minus 1, and then you get a range from -1 to +1. What if you need a range from -5 to +7? Okay, very simple. First, you create a range from -5 to 5. Okay, that's going to be 10 times the random function minus 5. And then you from -5 to 7. You need to create a range from -6 to 6, and then +1. So what you need to do is very simple. You have 12 times the random function, and then minus 6, and then +1. So that's it. All right, so you can create any range. For simplicity, I'm going to just use this equals rand from 0 to 1. And then I evaluate the function value here. That's simple. I just typed up this equation in the format of Excel. All right, in the format of Excel. I did this for the first row, and I double-click this. And I got all those numbers, and I got the sum here of this 125 numbers. Okay, unfortunately, this number differ from the exact value by 0.02. That's a little too much. So what do? I just do this random sampling multiple times, and then I get the average of it, and then the average is going to be good. So I actually did this 25 times. And you can see these 25 sums, they are all different, but look at the average. The average is pretty good. The average of these 25 numbers is pretty good. And also I can get more average. So I'm going to do a Control-C here. I copy this number and right-click. And be sure you right-click and choose 1, 2, 3 to get the numerical value. You can see, you can just keep clicking, right-click, 1, 2, 3. Right-click, 1, 2, 3. Right-click, 1, 2, 3. So just whenever you do right-click 1, 2, 3, it's an operation. And whenever you do one operation, the Excel actually changes all those random values for X, Y, and Z. And that's why you get different numbers here. All right, so look at this. Look at my number right now. The average of these numbers is 0.7628 compared to the exact value. Okay, let's do more. I'm gonna do more. It's a lot of fun to just do this. Oh, I forgot to copy this. Again, this number is not too accurate, but again, we just need to get more numbers. Just keep creating more numbers. You may find this tedious. Why do we need to create this many numbers, this many integral values generated randomly? This is because, again, first, we will have a really good accuracy here. Look at these two numbers. Very good accuracy. And two, look at the number of rows. We have only 125 rows here. All right, only 125 rows. So it seems counterintuitive. This is very complex equation, and I didn't use any bins with a fixed width. I just kind of randomly sampled 125 data points, within those ranges, and get those random, the function values of those random points, and I just sum it up. I got a really good integral values by itself, and then I get the average of how many here? Oh, we got 45, so why don't we get at least 50? Let's get 50. Okay, now we got 50. And I need to get the average of this 50. All right, look at this. Okay, actually, I think this number is still 0.001 off. Well, we may have to kind of do the average more times. Do this average more times to get 0.7623. But still, I just want to show you this method works. And also, more importantly, this method works magically for a function with 6 variables. 9 variables or even 300 variables without creating 10 to the power of 300 rows or 5 to the 300 rows. So if you have, like say 300 variables, my estimate is you probably need maybe 1,000,000 rows, and you need to do this sampling maybe at least 100 times. But look, 1,000,000 rows and 100 numbers here, 100 randomly generated integral values here, is still much better than 10 to the power of 300. So what is 10 to the power of 300? You need to say 1,000,000, million, million. You need to say million 50 times, okay? So that's why. And also, we're going to actually use this method to evaluate the electron-electron repulsion in the hydrogen molecule. Again, there are 2 electrons, so 6 variables. 5 to the power of 6 is 15,000. 10 to the power of 6 is 1,000,000. And we need actually 10 to the power of 6, 1,000,000 beans to get the repulsion reasonably accurately. But again, we do not want to create 1,000,000 rows. So we'll just use this Monte Carlo method to create random positions for electron 1 and for electron 2. So there are going to be 6 columns for 6 coordinates. We'll just evaluate the function to be integrated. In this case, it's the total wave function of the 2 electrons, psi, times the repulsion term, which is 1 over the distance between the 2 electrons. How do we do that? Well, after you create the random positions for electron 1 and the random position for electron 2, it's possible to use the square root of x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared to get the distance between the 2 electrons. That's simple geometry. And then 1 over that distance gives you the repulsion between the 2 electrons in the atomic unit. Remember, in atomic units, the charge of electron is just -1 atomic unit, and the electric constant is just 1. So 1 over 4 pi epsilon is just 1 atomic unit. And then we're not done yet. We need to multiply that by psi again. So it's actually psi star times the repulsion term times psi. And psi star is equal to psi because we will use a real function for simplicity. So it's going to be actually simply just psi squared times 1 over the distance between the 2 electrons. So we're going to use that to integrate the repulsion between the 2 electrons in the hydrogen molecule. And again, this is the Monte Carlo casino. It inspired mathematicians to develop this so-called Monte Carlo integration method to integrate those very high dimension functions. For example, in this case, 3 variables, and we can also evaluate the expectation value of the electron-electron repulsion in the hydrogen molecule with 6 variables for the 2 electrons. Again, you have 3 coordinates for each electron, and actually you can do multiple electrons as well.